For decades, quantum computing seemed like science fiction, a world where particles exist in multiple states at once, called superposition. These machines aren't just faster laptops, they're built to solve problems so complex that today's supercomputers would take millennia. This is the promise of quantum speedup, tackling challenges like simulating molecules for new medicines, optimizing global logistics, or breaking complex codes. Quantum computers use qubits to explore countless solutions at once, unlike classical computers that check one by one. But building and controlling these systems is incredibly hard. They're fragile and easily disturbed by noise. For years, the question was not just when, but if quantum computers could truly outperform classical ones. Now, on July 9, 2025, we stand at a turning point. A breakthrough has provided the first proof that a quantum computer can solve a problem exponentially faster than any classical computer. This landmark achievement confirms quantum computing's foundational principles are not just theory, they're reality. In science, unconditional is a powerful word. When researchers at USC and Johns Hopkins announced their result, it changed everything.
Previous claims of quantum advantage always relied on unproven assumptions, like the famous P versus NP problem. If someone found a clever classical algorithm, those claims could fall apart.
The new breakthrough eliminates that uncertainty.
The team mathematically constructed a problem that is hard for classical computers, based on established computational theory.
Their claim of quantum speedup doesn't depend on any unproven conjectures. It's a mathematical certainty.
That's why unconditional matters. It's the difference between thinking you won and holding the gold medal.
For the first time, we have a specific task where quantum speedup is a matter of fact, not belief. This provides the solid ground the field has been searching for.
It's a foundational theorem demonstrated in the real world.
How did the researchers achieve this? It started with designing a problem tailor-made for quantum power and provably impossible for classical computers to solve quickly.
They engineered a specific quantum evolution, a process where a quantum state changes over time, generating a complex, chaotic state that's nearly impossible to simulate classically.
They used IBM's 127-qubit Eagle processor, a leading device in the NISQ era. Powerful, but still noisy.
The team programmed their quantum evolution onto the Eagle chip, letting the qubits interact and evolve as planned.
The experiment's core was to measure the outcome, strings of bits whose statistical properties were the key.
The quantum evolution should produce a unique statistical signature. The team ran the experiment many times to see if the output matched quantum predictions.
The final step was to prove no classical algorithm could replicate these results. The data from the Eagle processor matched quantum predictions and was statistically distinct from anything a classical computer could generate. The quantum computer passed a test that classical machines were guaranteed to fail. One of the most ingenious aspects of this experiment was how the researchers handled noise, a notorious enemy in quantum computing.
Instead of fighting noise, they incorporated it into their problem.
They studied the specific noise in the IBM Eagle processor and designed their quantum evolution so that noise actually helped create the complex state they needed.
The noise acted as a randomizer, making the quantum system even harder for classical computers to simulate.
By leveraging noise, the researchers turned a weakness into a strength.
This approach suggests we don't have to wait for perfect, error-free quantum computers to see real quantum advantage.
It opens new research into noise-assisted quantum algorithms, potentially accelerating practical applications on today's hardware.
To appreciate this breakthrough, remember Google's 2019 claim of quantum supremacy with their Sycamore processor.
Google's result was impressive, but conditional, based on the belief that no classical algorithm could efficiently simulate their experiment.
Soon, IBM and others showed that better classical algorithms could narrow the gap, making the claim less absolute.
The USC and Johns Hopkins result is fundamentally different. It's built on a rigorous mathematical proof, not a race against current supercomputers.
The problem they designed has a proven property. As it grows, classical computers take exponentially longer, while quantum computers scale much more efficiently.
This is a permanent, unassailable gap.
This unconditional proof is the field's first unambiguous victory, a decisive demonstration of quantum advantage that will stand the test of time.
It's a definitive statement, not a contested one.
The insights gained will inform future algorithms that tackle real-world challenges. While the specific problem solved here has no immediate application, it's a hello world moment for provable quantum speedup. It justifies the massive investments in quantum hardware and signals that progress is real and accelerating. The result builds confidence and momentum for researchers, industry, and investors. This could lead to practical quantum advantages much sooner than expected, bridging the gap to future fault-tolerant machines. The technique of using noise as a resource could inspire a new class of algorithms for today's imperfect quantum computers. It proves the core promise of quantum computing is real, not just theoretical. This unconditional speedup is more than a single experiment. It validates the entire field of quantum science.
We are witnessing the birth of a new way to process information.
This breakthrough marks the moment when quantum computing's promise became undeniable reality.
For the first time, we can say with certainty that quantum computers can solve problems fundamentally beyond classical reach.
The techniques pioneered here will inspire a new generation of scientists and applications.
This achievement is a catalyst, spurring innovation and competition in the field.
The question is no longer if quantum computers can be faster, but how we'll use their speed to reshape our world.
The dawn of the quantum age is here, and it has just begun.